Hello, and welcome to my talk on VISCNN, a tool for visualizing interpretable subgraphs in CNNs. CNNs have become dominant models for a range of computer vision problems, but unfortunately, as is typical with deep neural networks, it can be difficult to interpret how they work. VISCNN combines feature visualization, pruning, and graph visualization in order to make CNNs transparent, intuitive, and quick to explore. Our tool can be deployed on a range of CNN architectures, but here we'll focus on AlexNet trained on ImageNet, regularized for sparse activations. Okay, our first method, feature visualization, concerns data representation. It tells us what features internal to our network are looking for. Take this classification layer unit meant to encode Springer Spaniel. With gradient descent, we can tune the pixels of a noise image to maximally fire this unit, resulting in a semantically meaningful picture, a picture of what this unit is looking for. We can get meaningful visualizations of units inside our network as well. This conv4 unit seems to respond to furry legs, and this conv2 unit to an oriented curve. So, feature visualization tells us what units inside our network represent, but how do they do it? What's the algorithm that leads to a leg detector or a curve detector or whatever else? Here it's useful to look at circuits, the wirings of 2D kernel weights inside our network. Each kernel acts as a spatial template for where different input features should appear. This diagram shows a detector looking for red in the top left and green and blue in the bottom right. The feature visualization for this circuit makes perfect sense given these kernels. We can add another feature to our circuit diagram and see how the two connect in the next layer, and data processing is still interpretable. Of course, the circuit diagrams of modern deep nets are way bigger than this. How can we systematically explore the circuitry of these huge networks? One possibility is to use neural network pruning. Suppose we want to understand how this mid-layer leg feature operates on images. It's got a lot of upstream circuitry. We need to know what circuits we should focus on and which we can ignore. Take this vertical line-ish upstream feature. What's its effect on our feature of interest? When an input image is passed into our network, the upstream feature is checked against all local regions of the image, creating an activation map. This map is ReLU'd and passed along, until we get our target feature's response. Suppose, though, that our vertical line feature were removed from the network. How would the response of the leg feature change? If we set the input activation map to 0, then run the model forward, the output activation map changes. Cool. What about this next input feature? We zero its map, run the model, and no change. So the first feature is important for how the furry leg detector responds, but the second feature isn't. We can apply this logic to all nodes in our network diagram, giving each a scalar importance weight. Edges pass activations maps too, so the same logic applies and we can weight those as well. Unfortunately, explicitly removing each node and edge then running the model forward would take forever, but drawing from neural network pruning research, we can approximate the importance scores of each graph component as its activations times the gradients from our target feature, averaged over the activation map and across images. Putting this all together, we get VISCNN. Here's a demo. First, we query the network for features important for border collie images, then multiple dog breeds, then for features important for dog breeds over and above their general importance. The tool can project network nodes in various ways. Here, based on category-wise importance, it seems dog features ended up in the bottom right. We can query based on other metrics, such as activations alone, or the graph components with the largest weights. We can click through the graph to visualize the activation maps and feature visualizations of nodes, and the tool can also display the most important incoming features from the previous layer. Similarly for edges, we can check the in and out activation maps, feature visualizations, and kernel weights. Changing the subgraph output checks graph importance for a target feature, as described in the pruning slide. We can feed different images into the network to check internal activation maps. Clicking on a pixel in an activation map reveals its receptive field in the input image. This feature likes black on brown fur, but not so much this trailer truck. If we instead query for graph components important for trucks, we find important features are at the opposite end of the representation space. We can explore these features in much the same way. This important intermediary feature seems to act as a wheel detector. Observe that our current queries don't really return subgraphs to our target feature. There's nothing preventing a dead-end node or a dead-end edge. We can fix this by first filtering for important nodes, then filtering for important edges connecting them. This method returns bona fide subneural networks that we can threshold to a desirable size. These subgraphs can be extracted, saving a new neural network that itself can be visualized in VISCNN. A good way to check the quality of an extracted subgraph is to revisualize the target feature using that subgraph. Qualitatively speaking, subgraphs extracted using our method preserve feature appearance well. Comparing a subgraph that captures maximal importance weight to a random subgraph of the same size, the difference is clear. A subgraph of the same size that captures minimal importance weight looks even worse. We can also visualize how features change as subgraphs get smaller. Here, each graph is a subgraph of the one before, resulting in an ever simpler degrading visualization. Conversely, you could think of this as building up a complex feature moving right to left. In some instances, subgraph visualizations reveal new meaningful aspects of the original feature. On the left, the extracted subgraph highlights an animal body. The subgraph on the right changes the orientation of a human face. We can be more quantitative when assessing the quality of subgraphs by looking at the correlations between their activations and those of the original feature. Here we sampled optimal subgraphs for all nodes in AlexNet. Optimal subgraph activations correlate nicely, better than random and minimally important subgraphs of the same size. You can try VISCNN for yourself at this GitHub link. Thanks.